For centuries, physicists have categorized the universe's fundamental forces into four types: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These four forces explain nearly all physical phenomena we observe, from the falling of an apple to the interactions of subatomic particles. But what if these forces are not the full story? What if there exists a fifth force, hidden in the shadows, subtly influencing the cosmos? In recent years, this possibility has captivated the physics community. This video delves into the idea of a fifth fundamental force, the evidence supporting it, the experiments searching for it, and what it could mean for our understanding of the universe. Before exploring the idea of a fifth force, we must understand the four known fundamental forces. Gravity, described by Einstein's general theory of relativity, gravity is the weakest of the four, but has infinite range and governs the motion of planets, stars, and galaxies. Electromagnetism. This force acts between electrically charged particles and is responsible for light, electricity, and magnetism. Strong nuclear force. It binds protons and neutrons together in atomic nuclei. It is the strongest force but operates over very short distances. Weak nuclear force, responsible for radioactive decay and nuclear fusion. This force also acts over extremely short distances. These four forces are described within the framework of the standard model of particle physics, except gravity, which is described by general relativity. The standard model has been enormously successful, but it is incomplete. Despite its triumphs, the standard model cannot explain several key phenomena: dark matter and dark energy gravity, not included in the standard model, matter-antimatter asymmetry, neutrino masses. These gaps hint at physics beyond the standard model. One such possibility is a fifth fundamental force. The idea of a fifth force is not new. In the 1980s, a team led by Ephraim Fishbach at Purdue University reanalyzed data from the Earth-WOS experiment, which tests the equivalence principle. They noticed an anomaly that could suggest a new gravity-like force acting over medium distances. Although subsequent experiments failed to confirm this anomaly, the idea lingered. A more recent and intriguing clue emerged from Hungary's Institute for Nuclear Research, known as Atomki. In 2016, physicist Attila Krasznahorkai and his team observed unexpected behavior during the decay of an excited state of beryllium-8. The results hinted at the existence of a new particle with a mass around 17 mega-electron-volts. This particle, dubbed X17, could be a mediator of a fifth force. If real, X17 would represent a previously unknown boson. It might couple weakly to electrons and neutrons, but not to protons, suggesting a new interaction not described by the standard model. Although these findings are controversial and have yet to be independently confirmed, the Atomki anomaly has revived interest in a possible fifth force. Physicists have proposed various theoretical models to accommodate a fifth force. These include U1 extensions of the standard model. This introduces a new gauge boson, often called a dark photon, which could mediate a fifth force. Chameleon fields, scalar fields whose properties vary depending on the local environment. These could explain why a fifth force might have evaded detection. Extra dimensions. Some string theory models suggest additional forces arising from higher dimensional physics. Each of these models predicts different interactions, ranges, and coupling strengths, leading to a wide variety of possible experimental signatures. If a fifth force exists, it must be very weak or act only under specific conditions, or we would have already observed it. It could modify the behavior of gravity at short or long distances, cause anomalies in the trajectories of spacecraft or celestial bodies, affect the decay rates of certain particles, interact primarily with dark matter or other invisible sectors. In some scenarios, The fifth force could even help unify gravity with quantum mechanics or provide a portal to a hidden sector of the universe. Around the world, experiments are underway to find traces of a fifth force. Dark light at Jefferson Lab and PADME at INFN search for dark photons. LHC, Large Hadron Collider, data is analyzed for signs of new light bosons. Satellite and planetary motion studies look for deviations from Newtonian gravity. Atom interferometry and precision measurements aim to detect tiny deviations from expected forces. While no definitive evidence has been found, improvements in experimental sensitivity continue to shrink the possible parameter space for a fifth force. Discovering a fifth force would revolutionize physics. It could open the door to a new branch of fundamental interactions, offer insights into dark matter and dark energy, help explain why gravity is so weak compared to other forces, enable a grand unified theory. It would also require us to rethink many assumptions about the nature of matter, energy, and space-time. Despite exciting possibilities, the scientific community remains cautious. Extraordinary claims require extraordinary evidence. Many reported anomalies in physics have later been attributed to experimental errors or misinterpretations. That's why independent replication and rigorous statistical analysis are essential. The Atomki anomaly, for example, has not yet been reproduced by other groups. Until it is, it remains a tantalizing but unconfirmed hint. The search for a fifth fundamental force reflects our never-ending quest to understand the universe. While the standard model has served us well, nature may still hold surprises. The idea of a hidden force, perhaps lurking in the interactions of particles or in the fabric of space-time itself, invites us to look deeper. If we do, it will not only reshape our view of physics, but also bring us one step closer to a more complete understanding of reality. Stay curious and keep exploring.